I need to feed your ego.
Yes, exactly. You need to feed my ego. Exactly. That's the trademark of a good teacher.
Let me go in.
How's it going, Grace? You can sit wherever you want. Okay, so how's it going, everyone? So to get started, what I want you to do is I want you to think about how fast do you think is the fastest human-made object? So do you think the fastest human-made object is 7,000 miles an hour, 17,500 miles an hour, 38,610 miles an hour, or 289,927 miles per hour? So how fast do you think is the fastest object that humans have ever made? There is quite a spread in the scale of these speeds. Um, so how fast do you think is the fastest human-made object? 7,000, 17,500, 30,610, or 289,927 miles per hour, which is pretty fast, I think. Let's take a couple more minutes for people to roll on in. We have a deadlock tie for answers right now. What people think. We have eight answers so far. One answer has four. The other one has four. The other two have 0. Let's see. Well, let's see if we can break the tie here. Oh, the tie was just broken. The tie is back again. We got 3 more votes. We got 4 more potential votes. For those of you just joining us, I want you to answer, how fast do you think is the fastest human-made object? We have a dead tie. One of them just took the lead. We have one answer with 6, the other one 5, the other 2 with 0. Ooh, it's 7-5 now. The lead is opening up. Can they 8-5? 8-5. The lead has opened quite a bit. Can the other answer pull back here and reclaim the tie? Oh, 8-6. Someone just voted for. We have 14 out of 15 people have voted. It looks like one answer has slightly prevailed here. We'll take another 30 seconds or so for the last 2 people to vote. Let's see if we can close the tie here, or if one answer will remain the winner. Oh, it's 8-7. It's been a deadlock this whole time, actually. 8-7. This could be a tie or a very, very, very slight win. All right. So it looks like that. Okay. So it looks like that 9 people have picked 38,610, with 7 people picking the 289,927 miles per hour. So, which answer is correct? We will reveal it in 1 second. But for now, here's what we're going to do today. We are going to be talking a lot about stuff in space once again. So one thing you should try to do is, I have a graphic organizer that you guys can fill out. I would highly recommend you fill it out because there's going to be a lot of things to write down. So I have links to the slides on there. I have a link to the video we're going to watch. So everything should be on there. So I would recommend you open it and make a copy of it. Yes. Okay. So Miles brought up an interesting thing. So there was a nuclear test, I think. I don't know how long ago what it was, but it was fairly recently. Miles, do you know when it was? It was fairly recent, I think. But basically, there was a manhole cover that was near the site of the test, and then the pressure from it launched the manhole at a speed of 125,000 miles an hour. Yeah. So you just had that thing open. Yeah. So, and so that was one of the fastest things that was ever created by humans. The actual fastest thing that was actually created was very recent. This is the NASA Solar Probe. So NASA Solar Probe is not a satellite, but it's a probe. It's like something launched in space to collect data and stuff. So that was actually launched in 2018. And it reached a maximum speed of 289,927 miles per hour. If you don't know that was 1957? Okay, yeah, okay, that's quite a long time ago. I thought it was actually much more recent. So the Solar Probe was launched in 2018, and it reached a speed of 289,927 miles per hour. If you don't know how fast this is roughly 12 times faster than the Space Launch System. The Space Launch System is the big rocket that NASA is currently working to develop, and that itself has a maximum speed of 24,500 miles an hour. So one of the most powerful rockets we've ever made had a speed of 24,500, and this probe actually has a speed of 12 times faster than the Space Launch System. In 4 years, in 2024, the Solar Probe is actually projected to reach 430,000 miles per hour, which, if you don't know what that means, that's 120 miles every second. So the question is, how is it so fast? So what I want to do is I'm going to put you in your groups here, and I want you to try to brainstorm some hypotheses for how the Solar Probe was able to travel at speeds 12 times faster than one of the most powerful rockets ever produced. So another thing that you may want to consider is that the Solar Probe itself is not powered, right? There's no rockets being attached to it. So how is this thing supposed to travel 12 times faster than one of the most powerful rockets we've ever produced? So I'm going to put you in your groups. Let's take 5 to 10 minutes or so, and let's see if we can come up with some ideas for how the Solar Probe was able to travel so fast. Oh, there's also not a lot of people today, so I'm gonna have to mix up some of these groups here. Uh, Okay, this should be good. Okay. Okay, so how did we make this thing go so fast? If you, one of the things that's really important here is that we physically cannot create this speed ourselves. We just don't have the technology for this. So we have to sort of use the physics around us. We have to sort of manipulate the physics around us to allow objects to move this fast. So um, before I actually tell you how this actually occurs, what I thought here was we would actually show a clip from The Martian. If you've ever watched The Martian, it's a great movie. Matt Damon gets stuck on Mars. That's pretty much the entire premise of the movie. But one of the main, there is a clip from here where they talk about something very similar. So we're going to watch the clip here, and then we're going to see if we can try to maybe try to delve into what the clip is saying a little bit. A link to it is also on YouTube. The link is also on the graphic organizer. So if you want to watch it from there instead, that might be better because otherwise it might be kind of laggy from my stream side.
It's a secret meeting.
How do you know that? Why does Elrond mean secret meeting?
The Council of Elrond is from Lord of the Rings. It's
Lord
the
of-
meeting where they
decide to destroy the One Ring.
I'm going to call something Project Elrond. I would like my code name to be Glorfindel.
Okay, I hate every one of you.
Well, Teddy doesn't even know about this yet.
I'm sorry, who are you?
This is Rich Purnell, Astrodynamics. Tell him what you just told me.
I can get the Hermes back to Mars by Sol 561.
How?
Could you stand right there for me, please? Thanks. Right there, great. And could you stand right there? Right there. Okay, let's pretend that this stapler is the Hermes, and you are... I'm sorry, what's your name again?
Teddy. I'm the director of NASA.
Cool, Teddy, you're Earth. And right now, the Hermes is headed towards you, starting its month-long deceleration to intercept. But instead, what I'm proposing is we start accelerating immediately to preserve velocity and gain even more. We don't intercept with Earth at all, but we come close enough to get a gravity assist and adjust course. While we're doing that, we resupply with the probe,
The Taiyang Shen.
pick up whatever provisions we need, and now we're accelerating towards Mars. Near Mars. Now, we're going too fast at this point to fall into orbit, but we can do a flyby.
or it's a flyby if we can't get lightning off the surface.
Watney would intercept using the MAV.
Oh,
And then we just head home. I've done the math. Checks out.
Rich,
Yes, sir.
get out.
what the hell is Project Elrond?
I had to make something up.
Yeah, but Elrond?
So
What the hell is Project Elrond?
so the main term that they use, you might not have heard it, but they used a term called a gravity assist. And they talked about it a little bit. What I want you to do is I want you to try to come up with a hypothesis for what this gravity assist means. So I'm going to put you in groups here, and then once you're in your groups here, and I want you to try to come up with an explanation for how what this gravity assist involves. How does it work? How did you create this gravity assist? So in a few minutes, let's come back here and let's see if we can come up with some explanations for this gravity assist. So I actually heard some really good explanations for what a gravity assist is. I'm going to let a couple of people share what they know about gravity assists. Walden, would you care to
Yep.
tell us what you said? Go ahead.
Okay, so the gravity assist is sort of like using Mars' gravitational pull as like a slingshot. So the rocket would go around Mars, and they'd have to use a lot of energy to do that because the rocket takes a lot of energy. But then they would use the amount of force going towards Mars and then push out because they use a bunch of energy from the rocket to catapult themselves back towards Earth. But that means they would also have to time it properly, otherwise they'd just go off into oblivion.
I couldn't have said it better myself. That was a really good explanation. Thank you, Walden. What I also liked was that this in our group too. Miles actually brought this up too. So James talked a little bit about this idea of force, and Miles also brought in this idea of a centrifugal force. Like when you're going in a circle, you sort of feel a centrifugal force, and that's also related to gravity. So, and we'll actually talk about that later on today. But that's pretty much the gist of it. I feel like you just stole my job now. So basically, in order to make the Hermes spacecraft a lot faster, the Hermes is the spacecraft they use in the Martian. What the NASA wanted to do is they basically wanted to slingshot Hermes around Earth. So basically, by slinging Hermes around Earth, it picks up a lot of velocity. It's basically like as you're going around, it gets a lot faster, and the amount of velocity it can pick up is a lot more than what you can attain with rockets themselves. Right. So with rockets themselves, we can only go about 24,000 miles an hour. With gravitational slingshots, we can go much faster than that, right? So in terms of the physics behind it, so why does this work? So one of the main mechanisms behind it is that is through something we learned about first semester, conservation of energy. Basically, what happens is when you slingshot the spacecraft around Earth, what happens is that the spacecraft gets a lot faster. And when an object gets a lot faster, it has a lot more kinetic energy because kinetic energy is the energy you have from speed. And however, what this means is that because this object gained kinetic energy, right, we have to get this energy from somewhere else. So energy can't be created or destroyed. So if the spacecraft were to the spacecraft were to gain kinetic energy, something else would have to lose kinetic energy. And in this case, what's happening is that the spacecraft is taking away kinetic energy from Earth. So basically, you're transferring Earth's orbital kinetic energy into the spacecraft. And one of the things that makes this work is that because the Earth is so much bigger than the spacecraft, right? The amount of kinetic energy that the spacecraft gains is very negligible compared to the amount of kinetic energy that the Earth has. So basically, it's like you're almost getting something from nothing here. You're technically not, so we're not cheating physics, but because it's so negligible compared to Earth, it's basically, imagine if you like plucked one hair out of your head, right? You did technically lose a hair, but it's so negligible that it doesn't really have an effect on you. And that's the same idea here. The spacecraft gains kinetic energy, but Earth has so much kinetic energy that it's basically negligible. Now, on the flip side, you can actually do the opposite. So you can speed up a spacecraft by taking away kinetic energy from Earth. To slow down a spacecraft, you can also give some of the kinetic energy to Earth in return. And this is something there's actually, and so one of the main techniques about, just like one of the techniques about speeding things up is using gravity. One of the main techniques about slowing things down is also through gravity, because when you speed things up or slow things down, you need to use a lot of fuel. And fuel, as we talked about last time, is a huge concern in terms of rockets and space travel. So we need to be as fuel efficient as possible. And by using gravitational fields, it's a lot more fuel efficient and it's a lot faster than just using fuel itself. So one of the main reasons why this actually works, the reasons why we can actually use gravity to speed things up and slow things down is that this is because the orbits of planets around the sun, they're not circular. In fact, these orbits are oftentimes elliptical. Well, they are elliptical. They're not just often, they actually are elliptical. So what I have here is sort of the orbits around different planets around the sun. And if you look at the orbits here, you can see that the Mercury has a pretty elliptical orbit, right? It's very ovular. It looks like very much like an oval. And whereas Neptune, the biggest one here, it is an oval still, but it's like a little bit more circular. And so some of these are the more, it's from the pattern it seems here, the closer you are to the sun, the more of an oval your orbit is. The farther away from the sun, the more of an oval you have. So basically, right, the orbits of planets around sun, they're all ovals. They're not circular. So why does this matter? So before I talk about why this matters, let's talk about what it means to actually have an oval orbit, or in other words, an elliptical orbit. So an elliptical, this just basically means oval. If you don't know what the word elliptical or ellipse means. So this is what I'm gonna do is I'm gonna introduce a little bit of technical terms. So in general, a revolving body's eccentricity can be described with the equation E is equal to F over D. So basically, this is what this is saying is the eccentricity of an ellipse, the eccentricity of an orbit. You can describe it with the equation E is equal to F over D, where E is the eccentricity of the ellipse, F is the distance between the foci of an ellipse, and D is the ellipse's major axis length. Do you know any of these words? No, you don't know any of these words. We're going to go through each one of these words one by one. But for now, I want you to write down the equation. E is equal to F over D, and write down what these variables mean. So what does E mean? What is F? Or what is E? What is F? And then what is D? And then what we'll do is later on, in the next few slides, we're going to actually look at what each of these things means. What does it mean to have an eccentricity? What does it mean to have a focus of an ellipse? What does it mean to have a major axis length? But for now, I just want you to write down this equation. What is the eccentricity of an ellipse? What are the variables, the focus, the major axis length? I'm gonna give you a few minutes to do this, and then we're gonna move on. I want to start talking about what these individual things mean, because I guarantee you, none of you, most people are not going to know what an eccentricity is, what the focal focus of an ellipse is, what a major axis length is, right? And you don't really study ovals a lot, but you do study ovals a lot when you get into planetary and space sides.
Mr. Hugh?
Mhm.
Is the foci of an ellipse just another way on saying the middle of it, like a focal point?
Similar. It's what an ellipse. So unlike a circle, with a circle you have one definite middle. With an ellipse, you technically kind of have two middles. I'll show you what that means in a second. So, and with an ellipse, we don't really care that much. So the actual middle of the ellipse, we don't care a whole lot. We actually care more about the two focal, which are sort of these other two. They're like sort of. I guess they're not. I don't know if the middle is the correct term. They're more like they're like two centers, I guess, of the ellipse. I'll show you a picture in a couple of slides, and you'll see what I mean by it. But in an ellipse, it's the foci isn't the middle, isn't the real middle. It's more of these like, yeah, it's hard for me to explain without a picture, but I'll show you in a second. But it's a good question. Yeah, so we want eccentricity is E is equal to F over D. E is eccentricity, F is the distance between the foci, or the focuses, and D is the major axis length. So a revolving body means that an object is rotating around something. And then we will talk about what this eccentricity means. So once you are finished with writing this down, the next box on the graphic organizer has the link to the simulation, which we're going to do. I'm also going to put a link in the chat right here about the simulation. So this simulation we're going to explore what it means to have an eccentricity of some orbiting objects. So on this particular simulation, once you have it open, you can see my screen, right? What you can do is you can actually change the eccentricity of this orbit. So you can just drag the slider around here, and then you can hit start whenever you want to see it orbit. So I'll just let you give you a few minutes to play around with it, see what happens. But what I want you to notice here is what happens to the orbits and stuff when you change the eccentricity. So if you see on my screen right here, I have an eccentricity of 0.56. And then you can actually change the eccentricity after this to see how the eccentricity changes it. So that's 0.56. I'm going to change it now to 0.9. And let's see if you can notice a pattern here as the eccentricity changes. So the first one had an eccentricity of 0.56. This one here has an eccentricity of 0.9. And the last one we're going to do here has an eccentricity of 0. So we're going to try this with an eccentricity of 0. And let's see what we get. Yeah, so this actually looks kind of like a basketball, actually. So if you notice here, what you'll see is that when our eccentricity gets close to 0, our orbit becomes much more circular, and as the eccentricity gets bigger, right, the orbit becomes a lot more elliptical. It becomes a lot more of an oval. And you can see that as I drag my eccentricity, these 2 points change. And we'll see what these points mean. But so just quickly, so from here, what I want you to do is I want you to note down what happens when you change the eccentricity of the orbit. And then I want you to try to come up with a definition or an explanation or something of what it means to have an eccentricity, what the eccentricity of an orbit means. So what do you think that this means? So once you sort of jotted down what you think the eccentricity of an orbit means, we're going to look at the next variable in the equation. So the eccentricity is the E variable, right? The E variable. And as you probably noted down, right, the eccentricity relates a lot to how ovular the orbit is. If the eccentricity is 0, the orbit is perfectly circular. If the eccentricity is really high, the orbit becomes a lot more elliptical. So the this eccentricity sort of determines how elliptical the orbit is. The next thing that we're going to look at is the focus or the foci. So the foci they're basically the 2 centers of an ellipse. So if we see the simulation here, if we go back to the simulation here, you see that this is one focus and this is another focus. And as I change the eccentricity, right, the distance between the focuses increases. And as I decrease this, the distance between the focuses decreases. So they're sort of the 2 centers in an ellipse, and they basically sort of determine how the sides of it revolve around these 2 centers. And we use the quantity f to measure the distance between them. So based on the simulation, what object would you say serves as one of the focuses in any planetary orbit? Right, so any planetary orbit is going to be elliptical, and there's going to be a couple of focuses that the elliptical orbit has. So based on the simulation, what object would you say serves as one of the focuses in any planetary orbit? Go back to the simulation here. What object do you think serves as one of the focuses in any planetary orbit? So what would you say serves as one of the focuses? I would say that Based on this, I would say that the sun is one of the focuses. So basically, right, if you imagine this as a planet, right, and this is the orbit, one of the focuses is going to be the sun, right? Basically, the sun itself is shaping the orbit of the planets, and the sun is going to serve as one of the focuses of the orbit. The last quantity we're going to look at is the term semi-major axis. So in a circle, so let's talk about circles first before we talk about semi-major axes. So this is a circle here, and we're going to use, and so in a circle, what we use is we use the term radius and diameter to measure sort of the, so in a circle, right, this would be the radius, and then this would be the diameter. Right, with the radius being the half of the length of the circle, and then the diameter being the full length. In an ellipse, we use something different because in an ellipse, one side of them is going to be wider than the other side. So to differentiate the two, we use the term major axis and minor axis. The major axis relates to the longer side. So in this particular ellipse, the one on the screen here, and the major axis is this way, and then the minor axis is top down. So the major axis relates to the longer side, and the minor axis relates to the shorter side. Now, in terms of orbits, we only care about the major axis length. So we only care about the long side of the ellipse. So to measure the distance, so when we use the term major axis length, we're really just measuring the distance between the two edges of the longer side of the ellipse. So we're measuring the distance between this point and this point. So we're basically measuring the quote unquote diameter of the major axis. So we're measuring the diameter of the long side. When we use the term semi-major axis, we're measuring the radius of the long side. We're basically measuring how long it is from the middle to one of these sides. So semi means half essentially, and semi-major means half of the major axis. And then when we look at the full major axis length, we're looking at the length of the wide, the full length of the wide side. So basically, the major axis length is the diameter of the ellipse, and the semi-major axis is the radius of the ellipse. So these are so this is something that because planetary orbits are elliptical, right? We use semi-major axis and major axis to actually measure the length of the orbit versus instead of using the radius, because the radius itself is not very helpful because it's not a circle. So to sum up the three things we covered the eccentricity, we covered the foci, which is the distance between the two focal points, and then we covered the semi-major axis and the major axis. So I just want you to, for this one, I just want you to try drawing an ellipse and see if you can help visualize what some of these things might mean. So I want you to try drawing an ellipse with an eccentricity of 0.5 and a semi-major axis length of 4. So if you aren't really sure what to do this, remember that one of the equations that can help us here is E is equal to F over D. E is our eccentricity, F is our focal length, and D is the length of our semi-major axis. So you're trying to draw an ellipse with a semi-major axis length of 4, and then the eccentricity it helps us determine basically how much of an oval this is, because that will tell you where some of the focal lengths are. So to sort of show you what this might look like on my side, what I want is I basically want a semi-major axis length of 4, So the sum of major axis length so tells us the difference between the middle and the length on the edge of the long side. And if an eccentricity of 0.5, what this means is that my eccentricity here is 0.5. And my semi-major axis length is 4. But this is 4. What I get is that my focal length is 2. So what this means is that the distance between the center and my focal point should be 2. So I'm basically drawing an ellipse that looks like this, with the semi-major axis length being 4, and then the focal point being 2. And then so when I draw an ellipse, this is what the ellipse might look like, something like this, a little off-center. Basically, yeah, this is what the ellipse might look like. This is what a ellipse with an eccentricity of 5. If I wanted to draw one with an eccentricity of 0, right, that would just look like a perfect circle. And if I were to draw an eccentricity of 0.9, that'd be a really, really, really wide and thin ellipse. So basically, the eccentricity just determines. The point of this is that eccentricity determines how elliptical the orbit is, because planetary orbits can differ quite a bit in their eccentricities. So we talked a lot about how the object orbits, like what kind of shape they orbit in, and we talked about how they orbit in ellipses, and we talked about why ellipses are important. But we haven't talked about why they orbit other objects in the first place. Why don't they just fall into the other object? Why don't they just stationary? So I want you in your groups, I want you to try to come up with an explanation for why objects orbit around a center, why orbiting objects don't remain stationary, and why orbiting objects don't just fall into the center of the orbit. So why do objects orbit around a center? Why do orbiting objects not remain stationary? And why do orbiting objects not fall into the center of the circle? And I want you in your group to see if you can come up with a hypothesis or an explanation for why these things orbit in the first place. So in terms of what actually allows objects to orbit around a center, what allows them to orbit around a center is basically the force of gravity. Basically, gravity is pulling all objects towards the middle of the orbit, and that sort of keeps them going. What someone brought up was this really good analogy. I don't remember what the sport is called. Walden, you might have to
I
help me
found
out
out
here.
the name. I found out the name of it.
You found the name?
Yeah,
What is it called?
it's called shot put.
Oh, but shot put is usually the one where shot put's not the one where it's attached to the ball.
This one, it says that it's like a metal ball, and it's attached to like another like a metal string or whatever.
Ah, okay, okay. It might be a different variation. Okay, yeah, I'm seeing it. I'm seeing it. Yeah, here we go. It's called a hammer throw. That's what Wikipedia says. It's called a hammer throw, but there's a shot put attached to it. Okay, so let me see if I can actually show you a picture of what this means. What this looks like. So in this particular example here, basically the idea is, right, you have sort of have a force being applied to sort of keep this object in an orbit, right? You're basically essentially pulling it towards you, but because the object is still moving, right, that's why it's not collapsing into you. That's why it's still moving. You're constantly applying a force to sort of keep it going in a circle. So the same analogy applies for the planets, right? So just like in a hammer throw, you need to apply a force consistently in order to keep that it's not a hammer, but it's like the ball going in a circle. The object orbiting the other object also needs a force applied to it in order to keep it in an orbit. Now, in terms of what a force actually is, we talked about forces earlier. But we never really quite talked about the definition. So what a force actually is basically just a push or a pull on an object, right? So when I apply a force on an object, it basically just means I'm causing the object to accelerate. So I'm causing the object's velocity to change. So if I can apply a force to speed up an object, I can apply a force to slow down an object, and as long as if something is speeding up or slowing down, there has to be a force applied to it essentially. Or if it's changing direction, there has to be a force applied to it. In terms of in nature, like in terms of on Earth and stuff, in space and stuff, there's a bunch of different forces that we can look at. Gravity, for example, is a major force. Friction is a force. Electricity is a force, etc. These are all kinds of forces. Now, in terms of when objects are rotating in a circle, you need to apply a centripetal force, which you may have heard of, or a centrifugal force, which you may have heard of. You have to apply that force to keep the object going in a circle. And that force is being applied directly towards the middle of the circle. So in the hammer throw here, the person is actually applying a force to pull the ball towards him. However, the reason why the ball doesn't just hit him in the face is because the object already has a velocity going to the side. So it's basically the force is being used to essentially change the direction of the ball constantly, and it's never really able to overcome the fact that it's already going in a circle. Now, the thing is with the centripetal force is the centripetal force itself is not a real force. You need a centripetal force. However, you actually have to have a real force responsible for creating this centripetal force. And in the case of a planetary orbit, the real force that is responsible for creating the centripetal force is the force of gravity. So gravity is actually producing the centripetal force you need in order for like the moon, for example, to orbit the Earth. So gravity is actually producing the centripetal force you need. Now you can actually calculate both the amount of centripetal force you need and the amount of gravitational force an object feels. So if I have an object that has a mass of m, that is rotating around a circle with a radius of r, and the object is moving with a velocity v, the object will feel a centripetal force of mv squared over r. So F subscript C here, that's just the notation we use to signify that the centripetal force of an object should equal its mass times its velocity squared divided by r. So this is the formula you use to calculate the centripetal force. that an object feels. This is also a way to, you can also use this to calculate how much centripetal force you need to apply in order to keep an object in orbit. So it sort of works both ways. It sort of works as in, this is the amount of force an object feels if it's already in an orbit, or you can also treat it as this is the amount of force that you need to apply in order to keep the object in this particular orbit. I want you to also notice here that the amount of centripetal force you need to apply does depend on the velocity and the radius here. If you can see that if the faster an object is, the more force you need to apply in order to keep it in that orbit, essentially. And the smaller the radius, so in other words, the closer it is to you, the more force you need to apply as well in order to keep it moving in that orbit. One thing I just want you to remind you of is that the centripetal force is not a real force in itself. You need to create the centripetal force from other forces. I think one good example of centripetal force besides the hammer throw is when you are, like, if you've ever driven a car and the car is making a really fast, sharp turn, right? What do? You usually play the game Pancake, right? I think it's called Pancake. I remember playing it recently, where basically you slide completely into the other person and you just like smash them against the window, right? Because so basically you're driving in a car, right, and then the car makes a turn, and then suddenly everyone just falls through the middle, and it just smashes the poor person who is on that side of the turn. So basically, if I'm trying to make a turn going, if I am trying to make a turn going, let's say hypothetically, let's say making a turn going this way, counterclockwise, right? If basically everyone is going to be smashed into the middle of this turn. So everyone's going to be collapsed against the left side of the car. So that's a good example of a centripetal force. And when you're in this car, you're actually feeling a centripetal force pulling you into the inside of the turn, and which causes everyone to sort of pancake each other and hit the poor person next to it. A good reason why you should wear seatbelts is so that doesn't happen. But everyone will actually slide towards the middle of the turn. So the next time you're in a really sharp turn and you feel yourself sliding towards the middle, or you feel everyone pancake each other on the back seat, I just want you to remember that is a centripetal force. You're feeling a centripetal force acting on you. Yeah. So in terms of planetary orbits, what actually causes your centripetal force is the force of gravity. So, and just like you can calculate the centripetal force, you can also calculate the gravitational force. So any two objects in the world, in the whole universe, any two objects will feel a gravitational force between them equal to Fg is equal to Gmm over r squared. Okay, that's a lot of different variables here. So make sure you write it down, and we'll talk about what each one of these variables mean. So Fg, right, this is just the force of gravity. F means force, and the small subscript g just tells us that this is a force of gravity. One thing I want you to remember is that this is not the same thing as F times G. This subscript notation can be kind of confusing. So F subscript G is not the same thing as F times G, right? It's like a little label for it. It's a label for the word F. So this, and the label here, the label G means that this is the force of gravity. And this is going to equal G times M over r squared. Each one of these is actually a different variable. Now, G is the gravitational constant. So capital case G is the gravitational constant, which is a number 6.67 times 10 to the negative 11. You don't need to remember this number, but I would write it down because you will need to use this at some point. So make sure you write it down. You can also Google this number. This number is also very easily Googleable. So if you ever just need to find the gravitational constant, you can just type in gravitational constant and Google will give you an answer for it. And so these are the units for it: meters cubed times kilometers, divided by kilograms, times seconds squared. Kind of complicated units. So this is a gravitational constant, which means that it's just a number. It doesn't change. You don't need to multiply it by anything. It's just a number. So you can just, if you want to just remember, you can just remember it as this number, 6.67 times 10 to the negative 11. That's just what the gravitational constant is. The other ones are variables. So the big M is the mass of the first object, little m is the mass of the second object, and r is the distance between the two objects. So in Gmm over r squared, G is a number, 6.67 times 10 to the negative 11. M is the mass of the first object. Lowercase m is the mass of the second object. And r is the distance between the two objects. So what I want you to note here is that any two objects in the universe, so me and the sun right now, I'm actually feeling a gravitational pull on it. I'm also feeling a gravitational pull from the next galaxy over, or 10 galaxies over. So any two objects in the universe is feeling a gravitational pull, including me and my water bottle. So I'm actually feeling a gravitational pull between the water bottle. And you don't have to be orbiting around another object to feel a gravitational force. For example, right, I'm not orbiting the Earth right now, but if I jump up, right, Earth is going to pull me down, and that's because Earth is exerting a gravitational force on me. Now, one thing I do want you to remember is that, once again, that the gravitational constant is just a number. It's not actually, it's not a variable. It is not dependent on anything. It's just a number, and the number is 6.67 times 10 to the negative 11. It does have units. The units are meters cubed over kilograms times seconds squared. The units are very complicated, so I just want you to be very careful when using the gravitational constant. I think worst case scenario, you just use it as 6.67 times 10 to the negative 11, and you just ignore the units because that might just be the easiest way. Sorry? Did you say something? Okay. Okay, so we're out of time here. It's 11:19. So we're going to continue the last part of this on Friday. So we're not going to finish everything today. There is no homework. Nothing is due. If you haven't submitted stuff, you should submit stuff though. Other than that, that should be it. And I'll see you guys on Friday.
Thank you.
Thank you.